It's a real pleasure to sort of talk about all the stuff that I've been doing for many years. The other thing I'm going to say is I need to, I have a very bad habit of making lots of slides. So you'll sort of, I'll be racing through slides and hopefully you don't get dizzy. I'll just try to keep in time. Okay, so I decided to talk about both input and output uncertainty, although I realize that probably most people are concentrating on output uncertainty, but I think half of it is the input. And so what I'm going to talk about is essentially, if you go to MICCAI these years, very often what you see, you have some intensity on the x-axis and you want to make a prediction on the y-axis. Maybe your prediction is a registration or a segmentation or a diagnosis or anything like that. And those little dots there, they're training samples. Then of course you use a neural network to sort of fit a curve through it in very high dimensions, obviously. And since a couple of years, people have found a good trick to sort of put uncertainty on that. So you have some error bounds. And so as I said, it's mostly deep learning and dropout at test time. So who has never heard of dropout at test time in a neural network? Okay, so I don't need to cover that. Yes. So what I'm going to do, I'm going to talk about these uncertainty bounds, but from a sort of different perspective, an alternative way using Monte Carlo sampling. And the other thing I'm going to do, what I've done now is kind of rotate this two-dimensional thing and make it a three-dimensional problem, because I think there's a lot of attention missing on this sort of this other direction that I put there, input variation. And so what we're really interested in is not just maybe sort of this black curve that I fitted through the points there, but I want to extrapolate this whole thing into spaces where I've never been before. And that could be, we're all aware, I think in MICCAI, that people have different imaging hardware, especially for something like MRI. That's a big thing. You also have different organs, different diseases, so there's lots of variation that people don't necessarily talk about, and I want to sort of talk about that. And so the way I'm going to talk about it is using generative models. I put there mutual information-based registration, N3 bias field correction, EM segmentations, etc. So maybe you don't think about mutual information as a generative model, but you can actually quite easily show that that you can come up with a model that does exactly that. And just to give you an example about, for instance, mutual information, it's quite amazing if you think about it, what it can do, right? You take two images, you don't care where they're coming from, which hospital, which scanner, what organ they are, you can register them, just like that. You don't need to retrain any network or anything. So there is some things I think we have lost over the last 2 years a little bit, and I'm going to try to push back a little bit on that. Okay, so I sort of have split the talk in two equal parts. One is about input uncertainty, and the other one is about output uncertainty. So I'll start with the input uncertainty. So what I'm going to mostly focus on is brain segmentation as an application, but really focused on a clinical setting, and that's important because it sort of changes the picture of what we're trying to do. And so we all know, how you can do things very nicely and very quickly using deep learning. You have a bunch of training scans with manual segmentations, and you kind of learn the trick of the blue arrow, and then you apply it to test cases, and that works. In a few seconds you get beautiful segmentations. It works very nicely. So in clinical imaging, it's a little bit more difficult than that. Okay, so maybe a first question that I can ask the audience. So if you think about the brain scan and there's a manual segmentation sort of shown, how long does it take one expert to actually generate this type of high quality segmentations for one scan?
1 hour.
Sorry?
1 hour.
6.
A week.
A week, yes, it's a week. So, it's super hard to do because you have like many slices and you go through them, let's say in a coronal view, and then you look at it from a sagittal point of view and it's completely garbage because there's no continuity. So it's very, very hard to do this in 3D very accurately. So that means that if you get A training data set of 20 subjects, it's amazing, right? Because it means half a year of someone's life that went into that. So, you know, we don't have much training data. The other thing, and I think many people are aware of that, you know, is that, yeah, different scanners, they generate different contrasts. So, you know, this is just a T1 weighted scan. You can see sort of what's going on. The thing that people don't talk about it so much is in clinical imaging, you have different, not just different hardware, you also have different protocols. So people might inject a contrast agent or might acquire a T1 weighted scan and a flared scan, or maybe not a flare, but a T2 weighted scan, or some diffusion. You know, there is lots of different combinations, and hospitals do change these protocols and change the sequences over the years. So there's lots of moving parts going on. And then finally, you have all these diseases, right? So let's say, so the top part is for MS, where you're interested in segmenting the lesions, the scar tissue in the white matter, but also segmenting 40 different brain structures, because people are interested in measuring atrophy in the gray matter. Or then on the bottom you have a brain tumor, so now you segment tumors and other things. So if someone approaches you with the data set that they acquired in the hospital yesterday of a patient and say, can you analyze this? Unless you have a generative model, you have to sort of say, well, I'm sorry, I need to retrain some networks, can you give me some training data? So there is a strong case to be made, I think, in clinical imaging to think a bit about the generative part. Okay, so what I'm going to do, I'm going to sort of use a toy example to introduce generative models. I think many people in the room will sort of already know what I'm going to show, so I'll probably fly through it pretty quickly. So the setup is that you look at one pixel in an image, and it has an intensity which I call D for data, and you want to find a label. I call L for labels in my talk. And let's look at brains. So we have 3 labels: white matter, gray matter, and CSF. And so discriminative models, you go straight after that. You try to model P of L given D, right? In generative model, you kind of go about it from a very indirect way. So what you try to do, you model the probability distribution of L and D together. And so one simple example is a Gaussian mixture model. So you have L on, the figure there, 3 different discrete levels, 3 classes. And each of the L's, each of the labels, the possible classes has a Gaussian attached to it. And so the product of these things give you a joint distribution. And you have a bunch of parameters. Those are the weights of each of the 3 Gaussians, and the mean and variance. So you can play with that to sort of make the model change. And then, of course, many people in this room will know that you can take a scan and actually fit the model to the data. You optimize the parameters of the model. And once you have that, then you can use Bayes' rule to sort of get a classifier. So you look at the posterior distribution of the labels. So what you really do is for every intensity D, you sort of look up, you take a slice out of this 2-dimensional distribution and you normalize. Okay? And then you curves. And then you can assign specific intensities to the label that has highest probability, and you apply it to your data and you get segmentation. Right? So, who has ever implemented an EM algorithm to fit Gaussian mixture model? Okay, most people, okay, some not, okay, yes. And so the whole trick, of course, is that now you get some different data, maybe it's an even T2 weighted scan, and you just repeat the process. You fit sort of the model to a specific patient. Okay, and once you do that, then you can sort of have a sort of dedicated classifier for every single patient. So there's good news and bad news. The good news is obviously it's adaptive, so you don't need much training data. The bad news is that you sort of have to always, for every individual case, optimize your model parameters, and that is slow. That's kind of the main sort of drawback, I think, about these methods. Okay, so what I'm going to do, so I described the baby version, now I'll sort of go to the full version. So this model, the Gaussian mixture model, is actually just an instance, a very simple one of a generative sort of process, where you have a distribution over L that models anatomy, and then given anatomy, you have a distribution over intensities. Given anatomy, it sort of models what happens if you put certain anatomy in a scanner, what sort of images, intensities do you think are going to come out of it. You have a bunch of model parameters that you can optimize. I won't talk about it too much. But sort of the whole idea is that there's a sort of firewall between modeling anatomy and modeling densities. And sort of by keeping those separate, you can sort of make adaptive models, which is very different from distributive models. The two are kind of smashed together. And then, of course, you use Bayes' rule, so you want something that has high prime probability and sort of matches well with the data. So here's our Gaussian mixer model with two Gaussians. Does it look like an MRI image? Maybe not, but you know, for simple cases you can use it. If we want to segment more cases, we need to have more complex models. So I'll quickly sort of describe some of the work that we've been doing to use whole brain segmentation. So we have a prior anatomy that's learned from 20 manually segmented cases, and it lives on a mesh, tetrahedral mesh, that can deform in certain ways, and we know kind of the average shape across individuals. And then we have these Gaussian mixture models. For every label, we say there is a Gaussian mixture model with parameters I don't know, and there is a model for bias field. And if you do that, then actually you can do stuff like this. So you have training data that was acquired in Boston 20 years ago, manually segmented by one very nice person who was willing to spend so much time of her life doing that. And now you can acquire your new data on your newest scanner with a completely different sequence, even multispectral, and sort of get these segmentations out. It takes about 10 minutes, so it's not 2 seconds on a GPU. So that's kind of the sort of the trade-off that you make. Maybe I should add that colleagues of mine, Adrian and co-authors, had a paper at MICCAI where they actually say, well, if all your images are, if you know what the acquisition was, and you have like lots of images of that kind, you can actually learn a neural network, teach a neural network to learn to predict the parameters of the model from the data, and then you can sort of cut this time down to just a few seconds. But then again, you're sort of trading off flexibility for a very narrow sort of application area. Okay, so if you go to clinical imaging, I've sort of described half of the problem, so we've kind of solved half of the problem. We can handle data coming from different scanners with whatever sequences people are using. But now, of course, in a clinical setting, you typically have sick people. So we need to sort of take care of how do we model pathology. And so generative models have this nice property that you can actually go in and sort of fiddle with them. So the way we did it is we have these sort of models for whole brain segmentation, trained on 20 subjects scanned 20 years ago, and we can augment it with a shape model of what a typical, let's say, brain tumor looks like. So we use neural networks to generative neural networks with some latent variables to really encode the shape and learn them from different subjects. So the trick is essentially that we don't need manual segmentations of anatomy again. We can use the old ones and just plug in another model trained on different subjects. So you have that flexibility. So in here is what you can then do. So this is a radiation therapy planning sort of problem. You have a brain tumor, but you want to also know where other structures are, such as the eyes and the brainstem, hippocampus, so that you can avoid radiating those. And so on the lower left, there is a manual segmentation, and then you can actually, with our tools, automatically, from a bunch of input scans, including even CT, generate a segmentation. And of course, you can sort of remove some scans, and people have shown similar things using neural networks, also at MICCAI a few years ago. But what's really cool is that you can actually take a completely new experimental sort of sequence and still get your segmentations out. So in this case, we just multiply T2 with FLAIR, but if someone has some data acquired at their hospital, we have a pretty good chance of actually immediately being able to analyze this data. Okay, so something completely else, but still related. So I work in a team in Boston that develops FreeSurfer, and so we've been using or developing a lot of tools to segment really tiny brain structures. And we've been using essentially this generative models to do it. So there's just these are zoom-ins into specific brain areas. So if you look at T1, they just look like a blob, like the hippocampus. But if you actually put things under a microscope, you'll see that there's different areas that do different things, and they communicate with one another. And so we can actually segment very detailed structures out of even blurry images. And we use exactly the same models. So you have these sort of mesh models that can deform. These are atlases, and I think they're quite pleasing to look at. Just that's why I want to show them. But on a technical level, there's sort of a very interesting problem you need to solve, and I think there's sort of two characteristics that really make it sort of push you in the direction of generative models instead of discriminative ones. And one is that the models that we build are built from dead brains, basically. So we take dead brains, take them out of the skull, cut them up, and put them in a bag, and put it in a 7T scanner for like a weekend. And obviously, you can do that with dead people because they tend to move. And you get these really beautiful images there, where you can then actually accurately delineate different structures. But let's say you wanted to, but then your in vivo scans, you can't make so long, so you get sort of these blurry type of things there on the left. And if you even if you wanted to use a discriminative method, you would have a fundamental problem, because you cannot just take a scan and wait for someone to die so you can cut open his brain. Right? So you can't get training data like that. You also cannot just take the ex vivo sample and put it with sort of your normal in vivo sequence, because the tissue properties have changed and the MRI contrast changes. So, you don't really have training data. It's kind of impossible to get it. And generative models, you can get around it. So here's just an in vivo scan. You can sort of delineate the structures. And the other part of it is that when people are really interested in the hippocampus, they do funny stuff. Like they get really specialized sequences, like there's a T2-weighted sequence there that really is centered around the hippocampus. It has thick slices, but really, or relatively thick slices, but very high input resolution. So you get sort of these beautiful details here. You can start seeing internal structures, layers within the hippocampus. And I can tell you there is no protocol, there is no standardization here. So people do whatever they can to get beautiful images. And then with generative models, we can say, okay, that's fine, send it to us, and we can actually automatically generate segmentations without retraining or anything like that. Okay, so I'm going to kind of completely shift gears. So maybe before I continue with the other half of my talk, I can ask if there's any questions at this point. No? Yep.
Yeah, so you said with your model-based approach that it was a trade-off in that you had to spend 10 minutes doing the segmentation, but what was the benefit compared to more modern deep learning methods?
Oh, so the benefit is that you can take any data and you don't need to retrain anything. Just, yeah, you're completely adaptive to this type of things, basically. Yes?
Just terminological clarification.
Okay.
You're using variability and uncertainty in an interchangeable way. But what we really mean here is the variability of the input, right?
Sure, yes, yes. Yeah.
So I just advise, I think we should make a distinction because the uncertainty has to do more with the interpretation. It's not that you don't know what is uncertainty, there's something you don't know. Variability means it's different, but you know what is the difference. So I think it's my opinion, I think it could be better to talk about that as a variability, because you do know the specifics of what is that variability. And in uncertainty, you don't know that.
Okay, sure. I'm not entirely sure that we know what the variability is. People send you data, you don't know what sequence they used, what scanner, you have no control over that. So but I'll take your point. Yes, good point. Thanks. Okay, I'll continue, and then maybe later we can have more questions if there's still. So I'm going to talk about uncertainty on the output now. So I've done I sort of was looking through the publications we've done over the years, over the last 20 years. And we've done lots of things, but one thing that struck me is that the last time I did variational approximations was 20 years ago, and then since then we've been doing lots of Monte Carlo sampling. And there is a reason for that, and I'll try to explain what those are. So let me first define quickly, I think everybody in the room will know what Monte Carlo sampling is. But essentially you get a distribution there, and what I want to know is sort of a bunch of yellow, white circles there, either just because they're interesting by themselves, or because I want to compute from average. Say, you know, if the function phi of x, which, you know, if x is a segmentation, phi would give a volume, what's the average volume of a structure that I'm segmenting? And so one nice thing about sampling is that if you have some variables that you don't care about and they end up in big integrals in your equations, all you need to do with sampling is just sampling from everything and ignore at the very end all the components that you're not interested in. So if you say you're only interested in the horizontal axis and not the vertical ones, you can take the white samples, ignore the vertical component, and you have samples from the distribution you're interested in, which is a very neat sort of way to get rid of things. And I'll come back to that. Okay, so you see a lot also at MICCAI, I think, variational approximations, which is a very different way of doing it. So what you try to do instead of sampling is say, well, I'm going to sort of decompose, I'm going to make an approximation Q that's just the product of two sort of lower dimensional distributions. So in this case, I have a two-dimensional problem. I'm going to try to find a Q of XA, which is one part of the model, times Q of XB, which is the other, has the other sort of components. And sort of try to use these sort of one-dimensional, to tune the one-dimensional Q distribution so that the product, which is shown on the right, more or less approximates what's on the left, right? And you do that in terms of KL divergence. And you can, I think you can already see kind of what the problem is that, you know, if you have strong dependencies across the variables, that's exactly what you don't model. So it's kind of an impossible task to sort of square. Okay, so here is essentially how I think about variational methods. So the good news is it's fast, right? It's like an optimization problem. You do it and then you're done. The bad news is it can be hugely inaccurate, so you completely underestimate uncertainty. And that's kind of a typical behavior of variational methods. So if you have strong dependencies among variables, which you typically have, your variational approximation is going to, you know, be very tight, basically. So that's shown there on the left. So it doesn't like to put a probability mass where the original model said there is none, basically. So then it effectively means that whatever is the shortest sort of distance of, you know, or the shortest width of your distribution is going to dictate your approximation. So that's a problem. And here's an example. I was really nice. You know, when I saw this in a paper from India a few years ago, I couldn't say I was surprised, but I was really happy to see that they did this experiment. So they actually had a registration problem, and they implemented, first they published a variational version of uncertainty, what's the uncertainty on the registration. And then they had a Monte Carlo version. You can completely see that, you know, this, if you can take this as the ground truth, which I think you can, then you get what they had with the variational method, essentially, is complete underestimation. And so I think there's two problems. One is that it's a general thing, and the other thing is that if you never implemented the Monte Carlo method, you wouldn't know. There's no red flags that, you know, if you have your method, derive your equations, implement variational method. There's no red flags where you say, oh, be careful, this is completely wrong, right? So at the end of the day, I think if you use this type of uncertainty to increase some dice score, something that people do with like dropout, I think it's completely fine. It's better than point estimates. If you really want to claim error bounds on something, I would be very, very careful with that. Okay, so here's just a quick slide about dropout. So if you think about the approximation they make there, it's unbelievably, I mean, it's kind of unbelievable what they do. Okay, so I would never, I mean, you can use it, and it's useful, but I would not relate it to the original Gaussian process that, you know, they try to approximate. It has nothing to do with that, I think. Okay, so I'm gonna So I'm going to quickly describe how Monte Carlo methods work in high dimensions. So in high dimensions, you cannot just sample from a distribution like this. You need to sort of be a little bit smart about it. And so the way it works is that you typically, you're in a certain state, and you have a proposal distribution. You propose a new state, in this case X star. And then there's this rule, Metropolis-Hastings rule, that sort of says whether or not you're going to accept this proposal. And I have an illustration here. So I start here on this white circle, and I've put a little Gaussian distribution as a proposal distribution. One standard deviation is given by this bigger circle there. And I'm generating a sample. So that's the red, so that's the black square there. In this case, it's pretty bad, so I'm not going to accept it. I do it again, that's even worse, I'm not accepting it. And then if you look at this Metropolis-Hastings rule, it says that even if it's bad, you can still sometimes accept it. So in this case, I'm going to accept this new proposal. And then if I keep doing that, I sort of get sort of these samples from my model. Okay. So all the white sort of points are would be samples. So the good news is you get really great approximations. If you do it long enough, you can get your approximations become exact, basically. The bad news is that whereas for variational inferences, dependencies caused errors, now they don't cause errors, but they make your sampling super slow. And so you can sort of see what's going on here. It has to do again with the width, sort of the shortest width of the distribution. So if proposals, you would like to make them big, to make big steps, but if you do that, you never accept your samples. So you're sort of constrained to very sort of tiny proposals. That means that in the long direction, you're doing a random walk, which is super slow. Okay. So I've only something like 5 minutes left, I think. Yeah. So I'm gonna talk about two things that we've used in practice. One is Gibbs sampling. Who doesn't know what Gibbs sampling is? Okay, yes. So it's a way to choose your proposal distributions in a certain way. So that's kind of what it's all about. And so the way you do it is, instead of a little Gaussian that you put around your current sample, you only look at one direction. So in this case, the first time you sort of look in the horizontal direction, you get a one-dimensional distribution that you sample from. And if you look into this Metropolis-Hastings rule, it will tell you that the probability of you having to accept that sample is 1, so you always accept. Okay? And then you sort of go in the other direction. Oops, sorry. And then you do the same. So now in the vertical direction, you do it again. And then you can keep doing that to sort of generate your samples. So this only works for certain problems if you can actually sample easily from the one-dimensional distributions. And there is a very strong connection to something like EM, but I don't have time, so I'll quickly skip over that. So I'll just show this. So this is an example, again, from brain tumor segmentation. So with this model with lots of parameters, and you sort of sample from many of them. The one thing you don't sample from is from deformation, because that's harder, and I'll show some examples later about that. Okay, here's another one. So my postdoc Michael has a talk later today in this workshop about formulating MI as a generative model. So then you can really sample from deformations in the mutual information. And you can do that with a Gibbs sampler. So we have an EM algorithm that works very quickly. It's like the Demons algorithm. You can kind of reuse the same software to a very large extent with the Gibbs sampler. Okay. So the last thing I'm going to talk about is a different sampler. It's a Hamiltonian sampler. So what you try to do is, you have a distribution, let's say a one-dimensional distribution, X. You're going to invent some new variables called momentums, which have the same dimensionality as X, and they're Gaussian. And instead of looking at the original problem, you can actually look at the sort of two-dimensional problem by taking the product. And then we already know if you sample from this two-dimensional distribution, if you ignore the samples from the momentum, you actually get valid samples from X. So here's how it works. So we look at the joint distribution. X is on the y-axis, M is on the vertical axis. So when we sample from it, we do a Gibbs sort of sample from in the momentum direction. So that's easy, that's just a Gaussian. And then we track sort of an isocontour in this two-dimensional case. And then we, okay, the movie doesn't stop now, but essentially when you stop, then you always accept. So if you look into this Metropolis-Hastings rule, you always accept. So if you concentrate on P of x, and especially minus log of P of x, it's essentially what's happening is that if I go up here, so we have a ball there living in some sort of surface, and I give a certain kick to the right, and I track sort of the movement of the ball. That's essentially what it's doing. Right? And then if I do it again, now I'm going to kick this ball to the left a bit harder this time, and I'm going to sort of track what's going on. Right? And so the amazing thing is that you can actually, wherever I stop this movie, I will accept the sample. So I can really cover large distances, and they're always accepted. And I see I'm out of time, so I'll just show you quickly some examples of how this works. So we did this work on hippocampal subfields. So it's a high resolution scan for the hippocampus. We have this model with meshes and mixture models. We fit the model to the data, you get a segmentation, but that's of course using point estimates there. So what if you're interested in having, not point estimates, but integrate out of all the parameters? So that we implemented something like that. So once again, we sample from everything, so the parameters and the labels. And here's sort of the deformation, a movie of the deformation. And then you can do stuff like this, where you get a brain scan. These are a bunch of samples from L, from the labels. You can really see where there's disagreement between the different samples of what the segmentation should be. Much more than if you use point estimates, obviously. And you can use that to sort of look at volumes. So point estimates are, tiny error. But if you really look at volumes, you can say, okay, I give you a number, but it's very blurry images, so I could be off by 10%. So it's very valuable information to provide. And if you use the mean of this sort of real distribution, you get a boost in performance classifying patients. And I think sort of this 1 to 2%, I think I see also in dropout papers for segmentation, uncertainty can boost you a little bit. Okay, I'm really out of time. I apologize for that. This is the last example. So this is a PET scan. It's also a generative model. We use this Hamiltonian sampler to actually generate reconstructions from projection data. And you can do this pretty quickly. This is on a GPU. You can get several samples per second. And you can do stuff like this. So you can see, if you scan 20 minutes, you have huge error bars in individual pixels. You say the mean sort of reconstruction, but I'm completely uncertain. If you increase the scan time, you can quantify. At 40 minutes, 60 minutes, you can sort of see these distributions go down. Okay, so, sorry, I'll quickly conclude. So what I've been doing is essentially, I've talked about uncertainty or variability on input. And instead of using variational methods, I've tried to advocate there is a place for Monte Carlo methods. And I've also talked about variability on outputs and variability on input. I sort of have been advocating with something else than discriminative methods, which is generative methods. And I think they're really complementary. So if you want to be able to say, write a piece of software like we do in free server, say, okay, send us, just download our software, throw your data in it and expect some results. I think there's a strong case to be made for generative models. If you have 10,000 scans in a huge study that you need to analyze and they're all exactly the same, of course you train a neural network, so it's kind of complementary. The other thing about sampling is that sampling is slow, right? So maybe it's not very useful, but at least if you make a variation approximation, do the sampling so you know what sort of claims you're making, what sort of approximations you're making. Okay, so that's it. I just want to thank the people who helped me with this and post an ad for postdoc like everybody else. Thank you.
still we have the time for one question, if anyone has any.
Well, I've always had questions, but I don't know. Yeah, one of the things in dealing with sampling is you can quickly, if the dimensionality of the space you're sampling in gets big, it becomes a huge problem. Can you just talk a little about that and what you can do about it? I mean, you showed very nice examples with 1 and 2 dimensional,
Right.
but often you have 6, 7, 8 dimensions.
Oh, sure. Yeah, that's easy. I mean, these models are like tens of thousands of dimensions.
Yeah,
the ones
okay,
that I
so,
mentioned.
but, okay, can you still talk a little bit more about it, because...
Yeah, so I think there's sort of 2 parts to the answer. One is that it depends what you want to use the samples for. If you just want to compute a mean,
it's trying to estimate the distribution, basically.
Right. So then it would be sort of use very smart proposals like this Hamiltonian sampler.
Yeah.
So you use essentially gradient information to sort of reduce random walk behavior. And I think that's kind of the state-of-the-art method for this time. Yep.
So when you were talking about the drawbacks of variational inference, you were kind of mostly talking about mean field inference.
Mm-hmm.
And it's, of course, the quality of your variational approximation depends on the model you choose.
Right.
So do you think that there is some other inherent limitations, or does it boil down to that we just always end up doing mean field because of the dimensionality?
No, I don't think so. I mean, like people use variational autoencoders. You know, in the sort of E-step of the EM algorithm, you use a variational approximation, the Gaussian. But then again, you know, actually in the paper of variational autoencoder itself, they show if you use a real sampler, you actually get better results. So there is always sort of this trade-off, right? They do it because it's fast, but then you lose some. Always, I think, unless your parameterization is exactly matched to the truth. So make a speed of that.
So let's thank our keynote speaker again.